Hello guys, welcome to another video from Computer Theory channel. In this video, we're going to solve the question number 5 of second chapter in Sipser textbook. And in this question, we want to train how to make a specific PDA or better I say Pushdown Automata for a given language. And yes, this is the question and let's solve it together. Okay guys, as you can see here, this is the question number 5. Give informal description and state diagram of Pushdown Automata for the language in exercise 2.4. That actually we solved this question in the previous video that we must give a specific CFG for all given languages, and now here we must construct the PDA for these languages here. So let's start with part A, which W contains at least 3 ones. So actually we know that the class of regular languages is a subset actually of context-free languages. So if we know that given languages is a regular language, we can construct it with a DFA and somehow change it to the PDA that we know that. So if we want to make a DFA for this language here, we need at least 3 ones here actually. So if we want to make the DFA, so let me actually make it clear. DFA, we need at least 3 ones. So here we will start with Q0, and after that we need at least 3 ones. So 1 ones here, after that another one, and after that the third one here. And this is our acceptable state here. So because after this state we have at least 3 ones in our languages here, and after that we can have anything. We can have 1 or 0 or other things. So yes, it will become like this. And we know that in DFA we must actually show all of the transition for our alphabet. So here actually we have 1s, or better I say 0 actually, and another 0 here, and another 0 here. And this is the DFA for the given language. And now we must do somehow actually change it, or better I say convert it to an equivalence PDA here. So we know that PDA actually, a transition on PDA have 3 parts. First, it reads the symbols that we can actually call it X. After that, it will look at the actually the first state, or better I say alphabet on the stack, and let's call it Y, and after that it will change the Y with another alphabet of our alphabet stack alphabet actually, and let's call it Z here. So yes, this is the transition on PDA. So because we construct the DFA for this language, all we have to do that we only need to read our actually string here. We don't need to write or pop anything from our stack. So our equivalence DFA actually PDA will become like this here. First we are in Q0. After that we must read 1 here, and we don't need to write or pop anything from our stack. So we can use from epsilon, and after that we are in Q1. We will read another 1 here, and we don't need to write or pop anything, and again we must only read another 1, yes, like this. And finally we are in Q3, which is our accepted state here. And for other actually transition, we can use something like this here. We can read 0, 0 epsilon, and 0 epsilon and epsilon. Here we have 0 epsilon and epsilon, again 0 epsilon and epsilon, and again we have 1 epsilon and epsilon, and 0 epsilon and epsilon. And yes, actually this is the equivalence PDA for this language that we have here. And yes, that was the answer for part A. Next we have part B. For part B, we must construct a PDA for this language, which W start and ends with the same symbol. And actually this language is a part of regular languages again. So we can somehow construct a DFA for this language and convert it to equivalence PDA for our language here. So if you want to make the DFA first, let's call it part B here. Yes, it will become like this, part B. And we need to construct a DFA for these languages here. Our language must start and ends with the same symbol. So first, let's build the DFA. We know that we will start with Q0. After that, we will see 1 or 0. So we have two options here, 1 or 0, and it will come like this. If we read a 1, we will go to Q1 here, and after that, we know that in this state we start our string with 1, so we must end it again with another 1. So whenever we read a 1, we will stay here like this, and if we read a 0, we must go to another state which is not one of our active states, that we can call it Q2. And when we read 0, we will stay in Q2, and when we read another 1, we will back to Q1. So it will come like this, and we know that Q1 is one of our active states here. So it will become like this. Yes, this is the actually ones part. For zeros part, we have something like this again. When we start with 0, we will go to Q3 here, like this. Yes. And after that, we know that Q3 is one of our active states, so it will become like this. And after that, if we read another 0, we will stay here like this. And after that, if we read a 1, we will move to another state which is not one of our active state, and we can call it Q4 like this. Yes. And if we read another 1, we will stay here. And if we read a 0, we will back to Q3. So yes, it will become like this. This is the DFA for given languages here. And now all we have to do is that we must convert all of this transition to equivalence PDA transition here, like before. So we must construct PDA here, that we will call it PDA. We will start with Q0. After that, we will read 1 or 0, so it will become like this and like this here. And if we start with 1, we will reach Q1 here, which is one of our active states. And if we read another 1, we will stay here, so it will become like this, 1 epsilon and epsilon. And if we read another 0, we will move to Q2 here, so it will become like this. We will move to Q2, and if we read another 0, we will stay here like this. And if we read another 1, we will back to Q1 here, and it will become like this. Yes, that was the construction for ones part, and now we must construct something like this again for zeros part. So we have actually Q3 here. We have Q3. If we read, and we know that it is one of our active states, if we read a 0, actually we will stay here like this. And if we read another 1, we will move to Q4 here. And if we read another 1, we will stay here. So we have this transition. And after that, if we read another 0, actually we will back to Q3, which is one of our active state. So it will become like this. But actually there is a point that I want to actually mention here, and it's that we know that our language must start and ends with the same symbol, and somehow we can tell this about epsilon. We know that epsilon is empty string, so it don't have any alphabet in it, and we can somehow say that it starts and ends with the same symbol. So we can have it here or not. It's actually something that depends on you and your choices here. That all we have to do, if we want to somehow count the epsilon, we must change our Q0 to one of our active states here. And yes, that's it. And that was the answer for part B. After that, for part C, W, which the length of W is odd. So for part C, actually, part C here. In this part, actually, I don't want to construct a DFA. We know that this language is one of our regular languages, but and actually we know that it is too easy to construct a DFA for this language, and all I want to do here is to directly construct the PDA for this language here. So W, which W is the length of W actually is odd here. So if we want to construct the PDA for these languages, it will become like this. We will start with Q0. After that, if we read 1 or 0 here, so it will become like this, 1 or 0. We will reach next state, which is Q1, and we know that here the length of our string here is odd, so it is one of our active state. And after that, if we read another alphabet, or better I say character, we will back to Q0 here. So it will become like this. And yes, this is the PDA for language in part C. Next, for part D, W, which the length of W is odd and its middle symbol is 0. So actually here we must notice 2 points here. First, the length of W must be odd, and next part is that the middle symbol is a 0 here. So if you want to construct the PDA for these languages, we can use the property of that. We know that the PDAs are non-deterministic. So all we have to do is that we need to find the middle of our string here. So if we want to construct a PDA for this language in part D, we can use from the non-deterministic property that we have here. We know that the length of our string must be odd. So somehow we can show the length of our string like this. Our length must be equal to 2k plus 1. Like this, and we know that k can be 0, 1, and 2, and etc. So yes, it will become like this. So we know that the middle point of our string is one of our alphabet in our string. So we can count it with 1, and the other part that will remain, the left part and the right part of the middle alphabet that we choose in our string. And we know that here this middle point must be 0. So all we can do here is that first we read the left part and add all of the alphabet that we read to our stack. After that, we can use from non-deterministic property to find the middle part that must be 0. And after that, for the right part, we can read the alphabet here and pop the alphabet that we add to our stack here. And when we reach an end stack, and finally, this is our active state here. So if we want to start, we will start with Q0. We can add a start symbol to our stack's alphabet here that we can somehow call it with $. So first we need to push dollar to our stack. So yes, it will become like this. Actually, yes, dollar. And after that, we are in Q1. When we are in Q1, all we have to do here is that we must push the alphabet that we read to our stack. So here we have these two transitions, 1, epsilon, and 1, and we have 0, epsilon, and 0. So with these two transitions, we will add all of the alphabet that we read to our stack here. After that, we must find the middle part. We can use from non-determinism here. We know that the middle part must be 0. So all we can do here is that we must somehow guess the middle point, and we know that it must be 0. So somehow we know that we must read a 0, and after that we read this 0, we can actually skip it and reach the right part of the middle point. So we can use from this transition to skip this 0, that is the middle part of our string here, and after that we are in Q2. In Q2, when we read any alphabet from our string, we must pop one of the actual alphabet that we add to our stacks, and finally we must reach the empty stack. So here it will become like this. We have all of this transition. When we see a 0 and the actually alphabet stack is 0, we must pop it. When we see a 0 and the alphabet stack is 1, we can pop it too. When we see a 1 and alphabet stack is 0, we can pop it again. And finally, when we see a 1 and alphabet stack is 1, we can pop it. And if we do all of this transition here, finally we must reach the empty string. Actually, better I say empty stack. And we know that with this transition here, we put a start symbol in our stack. And whenever we see this symbol, we know that our stack is empty. So finally, we can pop this symbol like this, epsilon, $, and epsilon. And finally, we are in Q4, which is one of our accept states here. So yes, that's it. This is the PDA that we construct for part D. Next, for part E, W, which W is equal to reverse of W, that is, W is a palindrome. We know that when the W is equal to reverse of W, we can call it palindrome. So again, for next part E, actually, yes, for part E, we can start to construct this PDA with this method again. We can actually start to read our string, and when we see any alphabet, we will add it to our stack, and somehow in the middle point, we will use from non-deterministic, and somehow we will guess that this point is the middle of our language here. So we have two options here. When our language is actually, the length of our language is odd, we know that in the middle point we have an alphabet, like before we have 0 or 1. And when the length of our language is even, we know that we don't have anything here. So we can use from epsilon transition to skip this part here. So our PDA must be something like this. First, we will start with Q1 here. After that, we must add the $, which shows the actual floor of our stack. So it will become like this. In here, we will reach Q2. Yes, it will become like this. After that, we must add any alphabet that we read here. So we have these two transitions here, 1, epsilon, and 1, 0, epsilon, and 0. And after that, we must guess the middle point of our string. So we can use from these three transitions here. If the length of our string is even, we don't have anything in the middle. So all we have to do is that we must skip a transition somehow, and we can show it with this transition, epsilon, epsilon, and epsilon. Actually here we don't read anything from our string, input string, and we don't look to our stack, and we don't pop or push anything from our stack. So here we have this transition, and when the length of our language is odd, we have two options. The middle point is 1 or the middle point is 0. All we have to do actually is that we must read this symbol and skip it. So it will become like this. We will read 1, epsilon and epsilon. We will read 0, epsilon and epsilon. So yes, this is the transition for middle part, and now we are in Q3. After that, when we are in Q3, we know that our string must be palindrome. So we have the two transition here. If we see a 1, we must pop it from our stack. When we see a 0, we must pop it from our stack. So we have these two transition here, 1, 1, and pop it, 0 and 0, and again we have to pop it. Let me fix this. Yes, it will become like this. And finally, if we reach the emptiest stack, we can reach our final state here. So it will become like this. And yes, that's it. Here we will reach Q4, which is one of our active state, or better I say, the only active state that we have here. And yes, this is the answer for part E. With this PDA, we can construct or better I say, recognize the palindrome string that we have. And for final part F, our language is the empty set. So for part F, as I say before, actually let me show you the part F. And we know that if we want to construct a CFG for this language, we can use from this CFG here. S will return S. And because here all we have that is variable, we don't have any terminal to convert our variables to terminal and finally reach a string. So we can't have any acceptable states here. So if we want to show the emptiest set with a PDA, all we have to do is that we must construct a state here, and yes, that's it. We don't have any acceptable states here, so it don't matter that what you do with your string, or better I say, the variable that you have in your context-free grammar. You can't reach any acceptable state here that you can generate a string with it. And yes, that was the answer for final part. I hope you guys enjoyed this video and learn a lot of these from this video for your exam, for your train. I don't know, you may have some preparation exam. And yes, I hope that it's be useful for you guys. If you like this video and subscribe to my channel, and you have any idea, leave it in the comment part. I will read all of your opinion. It is so good for me to read your ideas to somehow improve my channel, to make a better video for you guys. And yes, that's it. Have a nice day, guys. Goodbye.